Yes, class. Good evening. Am I audible to all of you?
Good afternoon.
All right. So Ahmed, Alan, Imad, Mariam, and Rehan have joined. Okay, class. So yesterday we had completed with the lesson ray optics. So in your optics unit, there are two lessons. One is ray optics, second one is wave optics. So wave optics is yet to be covered. Now see, from your second book, no, the topic that had the highest weightage was ray optics. It has a very good weightage. It's a difficult lesson, so do keep on practicing it simultaneously. I hope you had practiced it, but now also, along with the other lessons, keep on practicing it. Apart from this, then you have wave optics. Wave optics is not a very big lesson. We'll start it today. Obviously, not we'll be able to complete it today, but in the next weekend, we'll be able to finish it off. Then all the lessons that are now left from your second book, which includes your modern physics. Modern physics has 3 lessons: dual nature of radiation and matter, atoms, nuclei, and semiconductors. These are very small lessons that will take one single class for completion, most probably. Then your schedule is also there for test. I hope you all have seen. So now let's start with wave optics. So yes, in class in wave optics, you have 3 portions to be covered. 3 topics are there, subtopics you can say from this. Now from wave optics, first topic is Huygen's principle, which is present on the screen, Huygen's principle. Then after Huygen's principle, you have interference, then you have diffraction. So these 3 topics are present. Huygen's principle, interference, and diffraction. These are the topics that are present. Now, C class. First, we'll start with So we will start with Huygen's principle first. Now, Huygen's principle basically has one concept that you have to understand, which is the concept of wavefront. Now, if I have still water, if there is still water present, and if I drop a stone, then what is the observation that will be made by all of you? Still water is present and a stone has been dropped. Then what is the observation? What will you observe? Yes, class. Still water, when still water is present. And in still water, if you drop a stone, a pebble, if you throw a pebble on the still water.
Small waves or small?
Ripples, which you say, no? Yes, good imagine.
Yeah.
Ripples of water will be formed. So this is something, no, case like this only, let me tell you. Suppose let's say I have dropped a pebble. So what happens? Like this around it, in the still water, these will be the ripples that will form in the water, and rest of the water will be still. Wherever the disturbance has been created, that part only will get disturbed. Now see, wavefront is similar to this only. It's very easy to understand if you relate it with this and try to study. Now see, wavefront is what? This becomes the source. This is the source now. What is the source? Source that is generating the disturbance. Like here, when you had thrown the pebble, that only made all the ripples, right? So similarly, this is the stone. This yellow stone part is representing you the source of disturbance, you can say. All these waves, all these ripples that have been generated, all these portions, these are basically wavefronts, which we say, the term wavefronts. So wavefronts are what? Now understand it in terms of wave now. This was just general example. See, it is defined as continuous locus of all particles of the medium which are vibrating in the same phase at any instant. Like if I talk about right now, this particular time, if I talk about. So see, phase basically means speed. Here, phase means speed. So they are every particle that is present, it is vibrating with the same speed. So that continuous location of all the particles which you obtain, all the particles are localized at the point and they are vibrating at its own place like this. That you call it as the wavefront. Now, very important thing, rays. Because you have already studied about rays, here you will also be relating to rays and waves. Both the things you will have in mind. Rays are always perpendicular to the wavefront. Rays are perpendicular to the wavefront. Rays are always perpendicular to the wavefront. Like if all this is these particles, class C here, these are your wavefronts that are forming. Why this is the wavefront? It can be primary, it can be secondary. If this is created just because of this stone, let's say this is the source, which we are referring as stone. So all these disturbances that are immediately created here, all these disturbances which are at that present moment created, this moment, these are your primary wavefronts that are formed. If these will lead to formation of some other wavefronts, that we'll call as secondary, which you will see later on. Right now, just understand what are wavefront. So all these particles, these are forming your wavefront. And ray will be perpendicular to this. Each ray will be perpendicular to each of the particle. So wavefront is what? Wavefront, it is defined as continuous locus of all such particles of the medium which are vibrating in the phase at any instant. Now class, depending upon the source, you have different types of wavefronts. All right, whatever type of source you have. Like let's say a point source. Let's say we have a point source. So if you have a point source, the type of wavefront that you'll obtain will be spherical wavefront. So that is a similar case to the example that we had seen. See how? See, this is the source. Let's say this is the source. So these spherical wavefronts are created because of this source, and this source is a point source. Now, how will I draw the rays? These are all the wavefronts, these concentric circles that you are able to see, these are the wavefronts. Why? Because these have been created as a result of the disturbance because of this point source. So now these are the wavefronts. But if you want to draw all the rays will be like this. All the rays will be perpendicular to the source. So this red portion, these are the rays, while these are the wavefront. And this is your source, the point source which we are referring. So if you have a point source with you, so for the point source, all the sources disturbance that will be in the form of circle only. So we call that as spherical wavefront. So first type, spherical wavefront. Source is a point source which lead to formation of spherical wavefronts. Now, if you have a single point source, that will lead to formation of a circle, the way I had shown you right now. One more point source you take, that will also have its own circle. Then another point source you take, that will also have its own circle. So many point sources will be present, which will be having, each point source will be having its own spherical wavefront, correct? Every particle that is present, it will be having its own specific wavefront. Now, one point charge you take, one point source, not charge, one point source you take, it is having its own spherical wavefront. Another, I keep it over it, another spherical wavefront. Then I take another point source and I keep it over this. It will lead to formation of another source. if you notice, if I join all the point sources, that will lead to formation of a line. If you join all the point charges, even in your electrostatics, when you joined all the point charges, that led to continuous formation of charges. So same way here, if you look at the point sources, if I join all the point sources line by line, that will lead to formation of a complete straight line. Now see, so that if your point source is now replaced by line source. So for linear source, now see, it's like this is one point source with its spherical wavefront, right? One more with its spherical wavefront. If you keep it together, it will look like this, like the pile of coins. Coin will be appearing to you at the center. You will be having the source around it, that is the spherical wavefront, like this. These are all the point sources. Accumulate all the point sources together. Will not it lead to the formation of a cylinder? It will lead to formation of a cylinder, because every point is acting as a source, and that is having its spherical wavefront. So ultimately, this is leading to formation of a cylindrical wavefront. So the wavefront you're obtaining, this is cylindrical wavefront. And again, if you want to drop up the rays will always be perpendicular. Rays will be perpendicular to this. Then you have plane wavefront. Plane wavefronts are formed. So point charges we did, then combining all the point charges, that is linear charges we did. If all these point charges, linear charges, they are present at a very distant site, all these are present at a very distant site, that will lead to formation of a plane wavefront. These are possible for distant sources. These are possible for all the distant sources. So it's like it will lead to formation of a plane wavefront like this. Because point sources are at a very long distance sources are present. Now again, if you drop up the rays will always be perpendicular. So this rays will look somewhat like this. So such types are also formed, which we call as the plane wavefront. Now, apart from this, these are the three basic wavefronts that you require to understand. Point charges lead to formation of spherical wavefront. Then you had linear sources. Linear sources led to the formation of cylindrical wavefront. Then you had distant sources that led to formation of plane wavefront. These wavefronts are there three. Two more you require for your diagrams, for your understanding also, diverging wavefront and converging wavefront. See, diverging and converging. Diverge means what? Something that is spreading. Diverging rays we had. So see, if the waves are somewhat like this, now see, how will the rays be? So can you see rays are diverging? So from this only you can remember that all these convex parts that you were obtaining, that was diverging wavefront. Same thing if you take the opposite of it. Like this. If all these wavefronts, these are getting converged at a point. So for the rays also, what will happen? Rays also will get converged at a point. These wavefronts are known as converging wavefronts. Focus on this class that we are understanding the types of wavefront. We are learning here right now the types of wavefronts that are formed. So for the types of wavefronts that are formed, you have to understand these yellow portions that I have drawn. Those are wavefronts. Red colored parts are rays, ray diagrams. We have studied ray of light, any radiation, ray of light. That is the ray. Wave is different, wavefront, that is wave part is different, and the ray part is different. But when you combine it, diverging and converging more or less look similar only. So 5 in total you have. So wavefront was what? Continuous locus of all particles. in which every particle was vibrating in the same phase. It means with the same speed. It was vibrating with the same speed. And then you had these types, 5 types you have. Note this down, then we'll start with the actual principle, which is the Huygens principle.
Could you scroll up?
See, now coming to Heinz principle. So this was wavefront. What is the meaning of basic wavefront? Now, wavefront, basically how a wavefront propagates or how a wavefront travels, that is given by Heinz principle. Motion of a wavefront, forward propulsion of wavefront. So see how that occurs. See, let's say there's a point source. This is a source. And because of this source, there was presence of a wavefront, spherical wavefront was there. I'm just showing arc, not a complete one, but just assume that a complete circle is present. So source is there. This is the source. This is the first wavefront. Let's say this is t is equal to some 0, and we are calling this wavefront as the primary wavefront. Now, Heinz principle, what does it say? It says that on this primary wavefront that is formed, on this primary wavelet that is formed, see, this is continuous locus of all points. What did we say? What is a wavefront? Continuous locus of all points. So all these point charges, not charges, all these point sources are placed together. That leads to formation of a complete wavefront. So it means on this primary wavefront that has been formed, each point will act now as a new source, like a new source of disturbance. It means if I am referring, let's say this point will also act as a new source of disturbance. This yellow part that I'm showing, this is the main source that radiated this primary wavefront. But apart from this also, all the points that are present on this primary wavefront, that will also lead to the formation of some new waves. Like this will act as a point source. Now this is acting as a new source. This is again acting as a new source. This point, any point if you choose, all the points that are present, these are acting as new sources of disturbance. So if these are acting as new sources of disturbance, it means if this is again, let's say this is again a new point source. So another spherical wavefront will be drawn around it. So this means if you will draw, this will be a new wavefront that will be formed. This will be a new wavefront that will be formed. Here you will get a new wavefront. Here you will have a wavefront. This will lead to formation of the wavefront. This will be a wavefront. All these point sources, the way this orange line was the primary wavefront for this yellow source. Similarly, all these red dotted lines, these are now new wavefronts for these new point sources. Like this, all these will lead to formation of new waves. So this is now known as secondary wavefront. Wavelet, you can say, secondary wavefront, you can say. But now how did it move? If you join all the forward envelopes, these all arcs that are coming, if you drop tangent to the arc, this is the arc, if you drop a tangent like this, and you keep on dropping the tangents, and if you join all the points, see, if I join all the points, this will be somewhat like this. Like this, a tangent at this point, then a tangent for this arc, like this. Like this. So do you see? This is at t is equal to t. Initially, the wavefront was where? Initially, the wavefront was at t is equal to 0. Because of the new disturbances that are created, the wavefront we are able to obtain it here. Now what will happen? Again, all the points that are present on this new wavefront that has been formed, all these will act as fresh sources of disturbance. These will spread. Again, the forward envelopes you will drop. And what will happen? Like this, waves will propagate. Like this, waves will propagate if you drop the secondary wavefront like this. So this is what is Huygen's principle. So now let us read the points that are given. So Huygen's principle basically says that each point on a wavefront acts as a fresh source of disturbance called the secondary waves or wavelets. Understood? So each point on the wavefront acts as a fresh source of new disturbance, which we are calling it as the secondary waves, these new circles. Then it says secondary wavelets spread in all direction with the speed of light in a given medium, speed of light that is 3 into 10 to the power 8 meter per second. And the new wavefront at any later time, let's say t is equal to t, I had taken here, is given by the forward envelope. Forward envelope of the secondary wavelets at that time means tangential surface in the forward direction. So what does it tell you? What does Heinz principle tells you? It basically tells you about the forward propulsion or progression of the wavefront. So this is it all about the Heinz principle. This is just the Heinz principle. Now, based on this, you have some questions. Questions I'll tell you first, note it down. Any doubts you have, let me know. Otherwise, we now only have some theory questions. These are set-based questions that directly come. So note down this part, then we'll do a question. Done, class?
Almost done. It's finished. Done.
And what about others? Astha, Ahmed, completed?
Yes, ma'am.
All right. Let's practice the question which I was referring. See, in this, how the questions come, basically, these are fixed questions that come. All the parts I've already mentioned. Discuss the behavior of plane wavefront when it passes through first prism, convex lens, concave lens, convex mirror, concave mirror. All these mirrors, lenses, prisms, you have completed already. Now, for the first part, that is discuss the behavior of a plane wavefront when it passes through prism. It means the wavefront that is provided to you, this is already given, this is a plane wavefront. This is already given that this is a plane wavefront. So plane wavefront is present, prism is present. Now, how Heinz principle will be applied in this, that you have to see. So let us see the first part. See, for prism. This is incident wavefront, that is the plane wavefront. This is the prism. Now see here, the problem that will arise will be, this is a plane wavefront and all these prisms, convex lens, concave lens, these are not glass slabs that you will have uniform thickness everywhere. As you can see at the vertex of this, at the apex of this triangle, you will be noticing that this smaller glass is present. At the base is broader. So at the broader base, you have more amount of material present. So that's why we cannot draw a single wavefront. You have to choose 3 points. Let's say reference point I'm choosing A, B, and C. Now see, I'm just dropping an arc. I'm not drawing that complete circle. I'm just drawing an arc because obviously, you know, this here you have the source. So if you draw the complete circle, it will take a greater area. It's better if we just draw an arc. So see, let's say for A, this is the arc that has been cut. Leave B. See, for C point. For C point, the wave has to cover a greater distance within the prism only. Understood? Within the prism, the wave has to cover a greater distance. So it will stay a lot of time in glass as in comparison to A. So the radii will be a little less as compared to A. Now you join it. We drop the tangents to C. So this is how you get it. This is the final wavefront. This was the initial wavefront. And if you want to drop and see the path of rays, so see, rays are perpendicular. So firstly, rays will be like this. Rays will be coming like this and rays will be getting refracted at this particular point like this. Here. Same thing for this point as well. It will come here, it will get refracted. Like the same for B point. From B point also it will get refracted. These are rays, these are just rays. But mainly you need it for the wavefront. So prism is this. Now talking about convex lens. See, for convex lens, what do you have? This is the convex lens. This is the incident wavefront. Now see, again, if you choose these points A, B, C. So these are present at separate positions. Now see, for A point, see, this length is greater, means the distance that the wave has to cover is greater. So if you will plot the curve, the arc that will be obtained for this particular point, this will be at a greater depth. Like, see, this will be the radius that will be found. Now see, for B point, this thicker part of the glass part is thicker at the center because this is what type of lens? Convex lens. So you know the shape of a convex lens. Shape of a convex lens is like this. So the vertices are thinner, at the edges the lens is thinner, at the center it is thick. So if it is thick, this will cover a lesser distance, and this will again cover a greater distance. If you join all these arcs, you will get it like this. This shape you will obtain. And you already know convex lens was what type of lens? Converging lens. And this is what type of wavefront? These wavefronts, just now when we were discussing the types of wavefront, you have seen these are converging wavefronts. So these are converging wavefront. All these are converging wavefronts. So now if you drop rays on this, rays will be perpendicular to this. So convex lens will do what? It will converge this ray. Here it will be a straight line only. Here you have it. Again, it will converge it. See, like this, it will converge all the rays. This will be the path of the rays that will be obtained. Now you have concave lens. For concave lens, see, same thing will occur. For concave lens also, you have the incident ray, that is the plane. So for plane incident, you have plane incident ray with you, and otherwise you have concave lens. Now see, if you see the path of concave, if you just see the structure of a concave lens is thinner at the center, whereas it is thicker at the edges, right? So if it is thicker at the edges, the waves have to travel a greater distance when they are at the edges. Just opposite to the case of what you have obtained for convex. In convex, what happened? Thicker was the center, thinner were the edges. Here opposite happens, you know the shape of concave lens. So this will be the shape of concave lens. 3 points, again, just choose 3 points, 3 reference points. You can choose any other points as well. Now see, if you will notice here, this will be a larger depth. So this will be at this surface. This has to cover a larger distance. So this will be at this, or it's better if so see, now if you drop it, initially what had happened when you were drawing it for convex lens? See, for convex lens, at A point, yes, I'm repeating second part only. Convex, yes, second part only. See, for the edges, convex lens is thinner at the edges. So what is happening? At the edges, the glass part is very less. So the wave has to, or the ray of light, or you can even say the wave, that has to cover a larger distance in air as in comparison to glass. So it is formed at a larger distance. Because of the speed is high, it is formed over there. When you come to the C point, when you come to B point in the middle, the speed gets slower because the ray has to cover a distance that is larger in glass. So that's why it is formed near. This is all the rays are forming together only. See, rays are forming together. It's just that the ray that is passing through A point, it reaches fast, so it can cover a greater depth. Now what is happening? B point, for B point, it is covering a lesser distance because it has to travel a greater distance through glass. Yes, because it has to travel a greater distance through glass. That is the reason. Same thing if you drop it for concave lens. See, for concave lens, this time above part will take a lot of time, whereas B will allow it to be present. And same thing for C. Now, if you join all of these, if you drop a tangent, this will be the shape of the wavefront that will be obtained. So like this, you will have the rays and these are diverging. If you drop a perpendicular, automatically you will see that these rays are diverging. So this is the path for a concave lens. So prism we had seen, convex lens we had seen, concave lens we have seen. Now two are left, concave mirror and convex mirror. See, wavefronts. So these are wavefronts. Now firstly, we have convex mirror. This is a convex mirror. Again, choose 3 random points, A, B, C. So this has to cover a larger distance, B has to cover a lesser distance, and then C. C has to cover a larger distance again. So if you take C, see what will happen. The rays convex mirror does what? Convex mirror has the same function as diverging, right? Convex mirror, this has the same function as diverging. So when you know the final answer, that some rays are taking some time to be formed than the other rays, if you know, then what you can, I have drawn the arcs opposite. So what you can do, you can first directly draw for your examination point. Like I know for convex mirror, it is a diverging type because convex mirror is a diverging type of mirror. So you can do one thing, you can directly draw the diverging rays. Diverging rays I had shown you. This is how you draw for a diverging ray. Here, same thing for this lens, the way we had drawn for the diverging, this one. For diverging, we drop a concave lens like this. So if you drop it for a concave lens, same thing will occur here also like this. Because you know for concave lens and convex mirror, you have diverging form. So directly draw this first in your for your examination. And then you can show all these arcs. Because drawing in your exam, obviously you cannot have every time compass with you. So draw like this first when you know the final answer. Like for convex mirror, you know. For concave mirror, you know. For both the lens, you know. For prism, you are not sure. For prism, see what is happening because they can they can modify the prism. You can get any modification in the prism. Equilateral prism, you can get right angled prism, you can get isosceles prism, you can get. Do not, because we are not sure about it. So do not make such kind of thing in there. But when you are sure about the result, like convex mirror, you know these are diverging. So drop a diverging type of wavefront automatically first. Then your diagrams are systematical. Because you are not obviously using a protractor. You're not using a compass. If you're not using a compass, then directly use it. So here also, if you will see, this will be the path of the ray. And this will get reflected. Here, this will also get reflected like this. It will go. This should actually pass. No, this actually passes through this only, like this, when you plot it. And this will be a straight if you even plot it. Now, same thing if you have it for concave mirror. See if this is the incident wavefront and you have the convex mirror. Here you're having a concave mirror you're having. So see, for this part, this will be a concave mirror with polishing on the bulged part. So concave mirror does what? It converges. So draw this first by yourself. And then draw the arcs like this. Like this. Like this. Drop the arcs for it. And then like here also, by choosing all these points, A, B, and C points only. Now see, now when you will drop the rays, these will be appearing to converge at some point. But rays are different, wavefronts are different. Like this. So first tell me, all these 5 are clear. I'm again showing you. Let me know wherever you are having difficulty. See, for prism, any part you will get it like this. Here also one more arc you will have. Now what are these arcs? If this was A point, no, here this A point. So entire sphere is there. But instead of drawing this entire sphere, I am just drawing this much part. So that is what the arc is visible to all of you. Clear? Now see, so instead of this entire circle, you're just taking a portion of it. So prism is this. Any type of prism can come, just keep on drawing the rays. Wherever glass part is more, the radius will be less because it will take a lot of time to reach that point till the time A will cover a larger distance. Convex lens, same thing. You can initially draw it and then drop the arcs for a better ray diagram. Then this is concave lens, diverging rays with the diverging type of wavefront, and then convex mirror and the concave mirror. Tell me, is this part clear to you? Because questions from Huygen's principle are this only. Then you have to proving paths present. Clear?
Clear, ma'am.
Yes, ma'am.
Okay. Then write down the question because I think question also you all have not written. Note down the question and then write down all the parts.
Did we did anything else before this?
Huygens principles definition we did. What was the principle? And before that, the types of wavefront.
Okay, ma'am.
Done.
Almost understood. Almost done with the concave mirror. Done, ma'am.
Now there are two proofs that come in your examination. Refraction we have completed and reflection we have completed, right? Two phenomena we have already completed in ray optics. Now if it comes to relate both of these together, like you have reflection of light, which you have already studied using your lens. If it comes, prove it through Huygen's principle. That using Huygen's principle, you can prove that reflection of light exists. And how will you prove it? So we'll be just requiring the ray diagram for our purpose. We'll be just requiring our ray diagram for the purpose. This reflection on the basis of Huygen's theory. This is wave theory. So see, rest of the part, no, that is simple mathematics. This is not difficult. Just understand this patiently. You will be able to relate it. See, let's say this is some incident wavefront. This is the incident wavefront, let's say. Not incident ray, incident wavefront. This is incident wavefront. So if this is incident wavefront, obviously incident ray will be perpendicular to it. Rays are always perpendicular to wavefronts. So this is incident ray. Incident ray. This is incident wavefront. And class, incident wavefront's angle is always measured with the mirror. So this becomes angle of incident for the wavefront. For the angle of incidence, you know for the mirror, that is all made with respect to the normal, the angle that is made between the incident ray and the normal. But for incident wavefront, it is made using mirror. Let's say this is mirror M1, M2, this is some mirror. Because we are studying reflection right now. No? So this is a mirror. Now what will happen? Reflection will occur. Proper using laws of reflection, a reflected ray occurs. This is the reflected ray. Or even before the reflected ray class. See, this is the reflected ray. Now see, at all these points of the reflected ray, incident wavefront was there, incident ray was there. Why incident wavefront? Perpendicular to it was incident ray. Now, all the points that are present on the reflected ray, these will act as fresh sources of disturbance, right? Let's say I'm taking one point here and another point I'm taking it here. This is one point, this is another point. This is A, this is B. So one arc, let me take it here, and one arc I'm taking it over this side. So if I join this, or let me draw it a little nearer. I'm drawing the reflected ray first. A reflected wavefront first. Otherwise, this becomes very difficult to draw with the arcs. Fine, now I'm dropping the arcs. So for A point, let's say this is the first arc, and for B point, this is the arc. Because without arc, firstly drawing arc, then it becomes difficult to join. So this was the reflected ray. This is the reflected wavefront. Fine, this is the reflected wavefront. So then reflected wavefront is present. Then you'll again have incident ray, incident wavefronts. Let's say from this particular point here, you have an incident wavefront. This is an incident. This is again the same incident wavefront. Now again, this will get reflected. Each point on this will be having its own new disturbances that will again lead to reflection. Reflection will occur, reflected wavefront will occur, and so on. This phenomena will occur. Let's say this is AB. So let's name this as A, B dash. Now see, these travel with the speed of light. If these travel with the speed of light, then all these reflected wave, distance will be what? Distance is always speed into time. So let's say this is VT and this is also VT. This entire distance, AA dash and BB dash, this is VT. And class, this is angle of reflection, angle of incidence, and this is angle of reflection. See, this is angle of incidence and this is angle of reflection. You take it from the mirror. Do not take it elsewhere. Take it from the mirror. If you take it from the mirror, then only you will be able to notice that the angle of incidence and the angle of reflection both are actually lying along the same plane. Now see, certain proof we have to see. Just look at one thing. See, this incident ray will be perpendicular to this and this will be perpendicular to this just now. Now look at this point, class. Look here. This angle A and this angle B dash, both are equal to 90 degree. One thing, this angle, this is equal to 90 degrees. Secondly, BB dash and this AA dash, both are equal to VT. It means this has the same distance. If it has the same distance, it means both the rays are equal. Also look at this ray, BA dash. This is the common ray. So BA dash is one side, common side. BB dash is equal to AA dash, same side. And angle A is equal to angle B because they are equal to 90 degrees. So SAS similarity. Can you notice this triangle and this triangle both are similar? Now see, now look here. If you look at triangle BAA dash and triangle BB dash A dash, these two triangles that are overlapping. Firstly, BB dash is equal to A dash because both are equal to VT. Then look at angle A and angle B. Angle A is equal to angle B dash because both are equal to 90 degree. And BA dash is equal to A dash B. That is, both are having the common side. Now see, it means triangle BAA dash is similar to triangle BB dash A dash. Both the triangles are similar to each other. If they are similar, it means the rest of the things which were not even now similar, now it will be similar, which were earlier not similar, now it will be similar. It means this side, this AB will be equal to B dash A. Apart from this, B dash A dash A, whatever it is left. Notice this angle will now be equal to this angle. It means here, if you look, angle of incidence is equal to angle of reflection. So angle of incidence is equal to angle of reflection. This was one of the laws of reflection. So you can prove reflection on the basis of wave theory by this only. This shows that angle of incidence is equal to angle of reflection because both the triangles are now similar. And this proves the laws of reflection. Clear, class? One more part we have for refraction. Refraction, I'll tell you later. First, draw it for the reflection. Any queries you have from the reflection part, let me know. Then we'll come to refraction. That will end your Heinz principle. That is the first topic, Heinz principle. Yes, class. Now refraction on the basis of Heinz principle. So again, same thing. Diagram you have to see, rest of the derivations will be based on the similarity of triangles. Let's say this is a normal that has been dropped and an incident ray is incident on it. Now, refraction will occur over here. Now, refraction will occur from this part. This is the incident ray. See, this, be precise when you are mentioning the ray, when you are mentioning the wavefront. This is incident ray. Let's say here, refraction occurs. At this particular point, here refraction occurs. This is the refracted ray. Incident ray will obviously be perpendicular to the ray. This is both are perpendicular to each other. So this is incident wavefront. This is incident wavefront. Now see class. Incident ray came, it got refracted. Incident wavefront was present. Now again, I'm drawing the ray first because as I've told you, it becomes difficult to drop it. Now I'm drawing the arcs. Like this. For this particular point and for this point, name it something. Let's say this is A, this point is B. So for B, we'll drawing an arc. See class, these arcs, the circular parts are made first. Just for the convenience of the diagram, I'm drawing it afterwards. You can draw proper two arcs and then join it. Usually it becomes difficult to draw, especially on screen when you're drawing it. So otherwise, the method I'm telling you, for your exam also, you can do the same thing. Nobody is going to check which step you had performed first. Ultimately, your diagram should be neat and all the rays should be visible. Fine. Now see again, incident ray will be incident at this particular point. The ray will be incident. Now incident ray will fall here again, a normal will be dropped. This will be the reflected ray and so on. It will keep on moving. Propulsion is happening. Can you see the waves are actually moving? Same phenomena will occur at this end, same thing, then occur at this end like this, waves will keep on moving. Let's name this again something. Let's say this point is A dash, this intersection point is B dash. See class, this is the incident ray, this was the incident wavefront, this was the refracted wavefront. This was the refracted wavefront. This is again the next incident wavefront and so on. So angle of incidence, I have told you that we take it from the surface for the wavefronts. This is not the incident ray. Incident angle is this. This is different. This is incident angle of incidence for wavefront. And this is angle of refraction for the refracted ray. Second one. This will be perpendicular. Both these are perpendicular to each other, 90 degrees. But see class, here if I write VT and here if I write ET, will it be justified? See, speed is obviously different. Can you notice the speed is different? That's why it is intersecting over here. The arc we had obtained. Here the speed is more. Understood? Speed is more over here. That's why not reached it at a faster pace. Let's say this is some V1, V2 where your V1 is greater than V2. Now you cannot take it as VT the way you had taken it earlier in your last question. This is some V1T, this is some V2T because the speeds are different. And obviously refraction, continuously we have been studying rarer and denser surface. So mark this as N1, let's say this is the denser surface. So N1 and N2, both are the surfaces. These also you have to keep in mind. So I think rest of the things I have told you. Refracted wavefront is also there, incident wavefront, incident ray. This is the refracted ray. This ray is the refracted ray. Now, in this triangle which you see BAA dash, this triangle which you see BAA dash, see what will be sin I? Sin I will be perpendicular by the hypotenuse. Perpendicular is this AA dash, that is V1T, and hypotenuse is BA dash. Agreed? Sin I is V1T perpendicular by hypotenuse, that is BA dash. In the triangle B dash A dash, the lower triangle with having the angle R, sin R will be perpendicular by again hypotenuse. This time perpendicular will be V2T. So perpendicular by hypotenuse, that is BA dash. Agreed till here? Now see, let me write it first. Look here. In triangle BAA dash, sin I will be perpendicular. That was present here. If you see, that was V1T. AA dash by BA dash by symmetry. AA dash was V1T. And BA dash is, let's write it as BA dash only. In the next triangle B dash A dash, yes. Sin R, if you see, that is equal to B dash perpendicular by hypotenuse, that is BA dash again, and BB dash is V2T, so by BA dash. Now take their ratios. So sin I by sin R, this is equal to V1T by BA dash multiplied by BA dash by V2T. So T gets cancelled, BA dash gets cancelled. You are left with V1 by V2. Class V1 by V2 is already equal to N2 by N1. This is a relation that we already know. This is a formula. Keep it in here. Sin I by sin R is equal to N2 by N1. Can anyone recall? Is it some law? Is it some formula? Any law is this? Snell's law. Yes, correct. So this is Snell's law. So Snell's law is proven. Your refraction part is true. So both the laws are proved. One law was Snell's law out of the refraction law, and the angle of incidence is equal to angle of reflection. That was the law from the reflection part, because obviously angle of incidence and angle of refraction are not equal. No, angle of incidence and angle of reflection are equal. So that's why we had to prove Snell's law over here. Fine, class. Note down this part. And class, Huygen's principle, no, whatever you are writing right now from these notes, as it is will come. As it is, it comes in your exam. Prove refraction on the basis of, or discuss the behavior of incident wavefront when it is incident on a reflecting medium, like this, same thing, just same proof. See, did you not notice all the questions were exactly same? Otherwise, questions from Huygen's principle that have come, no, that are from your dual nature we have not done. No. Dual nature we'll do. Those are similar to dual nature. Speed is equal to product of frequency and wavelength. So that you already know, and that we'll do in dual nature of matter and radiation and matter also. But specifically, questions from Huygen's theory are these only. Those ray diagrams which we did, reflection and refraction, these two. And class, theoretical part from your wave optics will be there, especially from your Huygen's principle.
Ma'am, can you scroll up? A little down.